Hi everyone, I hope you're all doing well today. Welcome back to our applied mechanics lesson. This is part 2 of our vectors. In part 1, we essentially went into calculating the magnitude of our resultant force, and we went into the steps which follow to essentially get to this point. You'd first need to have your diagram, of course, and then you would need to calculate or come up with your components, and then we essentially sum up our components in order to come up with a final resultant force as such. So from this resultant force that we see, what it tells us is on the x-axis we have a negative, although on the y-axis we have a positive. So we'll try to represent this as best as we can. Negative 38.927, we could put it somewhere here. Okay, we can put it somewhere over here. Then positive 312, it is significantly higher, but we can just put it somewhere here for purposes of 312, 132. My handwriting is getting a bit dizzy. Okay, essentially wherever they meet, sorry, then you can extend your resultant force line from that point. Okay, then we end up with a diagram that looks something like this. Then of course here we have an angle theta that we don't know. There's a 90 degree. This angle here, it exists, but it'll be neglected for now. Okay, then next we are essentially gonna take a couple of steps that will help us figure out this angle theta that we have on here, and then we'll also need to figure out the magnitude of this line. So we could just label this side A, side B, side C. Okay, we already know side A is 38.927. We already know side B is 312.132, but we don't know what side C is. But from doing maths and from getting to this point, you would see that if we have a right angle triangle, an X is missing, we have A, we have B. What's essentially missing is our hypotenuse. So now we're trying to figure out the magnitude of this specific line that we have. And the reason why we need to do that is because our resultant force on here is still in terms of x and y. We still don't know the value of our resultant force, and I don't know how you'd go about asking people to fabricate a specific material if you don't know the exact strength that material needs to possess. Because at the end of the day, you are designing all of this, or you are coming up with all these numbers so that you're able to determine how strong a material needs to be to withstand certain forces. Okay, so essentially this is why we're carrying out this exercise. So knowing this, and from the theorem of Pythagoras, remember from your theorem of Pythagoras, it will tell you that your a squared plus your b squared will equal your c squared. That's essentially how you carry out your theorem of Pythagoras. But we are now looking for our c in terms of our hypotenuse, so you can manipulate the equation so you end up getting c as your subject of the equation. Okay, so essentially what we have is c squared is equals to a squared plus b squared. Then we know to get rid of the squared, you can introduce the root sign on both sides. So essentially we'll have that it'll be equals to c. Okay, then we have the value of a, we have the value of b as well. Then we can substitute to essentially get the value on there. Okay, then our value is 38.927 plus 312.132. Remember that squared, and all of these are to the root. Okay, then you take your calculator and very carefully plug and play everything that you have on here. Squared plus 312.132 squared. Okay, then C gives me 314.55. Okay, But remember, in as much as we're calculating it as a dimension of this triangle, C essentially represents your FR. So this means if this is anything to go by, then it means our FR magnitude will be 314.55. Ooh, my 5 looks dizzy. 0.55 newtons. Okay, then you would have essentially answered the first part of the question. You now have the magnitude, but now we need the direction, and the direction will be led by this angle theta that we have on here. Okay, then we're moving on. You'll remember our SOHCAHTOA. We'll keep referring to it. It looks like that X that just refuses to go away. SOHCAHTOA. Okay, so by looking at this specific triangle on here, our sine of theta would be opposite over hypotenuse, so it would be B over our resultant FR or a C. Okay, then our cosine would be adjacent over hypotenuse, which would be A over FR. Then our tan would be opposite over adjacent, so it would be B over A. Okay, you can use any of those ones to get the angle that you're looking for, but I feel like this poor child here by the corner, shame, let's give them a moment to shine. Let's try it with the tan. Okay, so we'll say tan of theta will be B over A. Okay, and our B, which was essentially the height all the way to 312.132. Then our A was 38.927. Okay, that's our tan of theta. Then our theta will essentially be the shift of tan over 38.927. Then you plug and play this into your calculator, or plug this into your calculator. Then I get an angle of 82.891 degrees. Okay, and it looks like it's the end. It looks like we're done, except you'll remember that our 0 or 360 line is here, and that angle we just got is from our 180 line over here. So it's at 82.891, and essentially we're looking for this one over here. You wouldn't be wrong if you left it at that, but you would of course need to make sure that you specify the direction as well, so it makes sense. So the last itty bitty step would be to say 180 minus your 82.891. Then you'd get a 97.109 degrees. Okay, then to finalize or to really answer your question, then you can say FR has a magnitude, okay, I won't write everything out in full, magnitude of 314 point, where did it go, 0.55 newtons, and it has a direction of 97.109 degrees from the positive x-axis. And then you would have answered the question. You would have your magnitude and you'd have your direction, and that's essentially how you go about solving for your vectors or calculating the magnitude and direction of your vectors. If you have any questions, you know what to do. Till then, adios.